Hi everyone, Dr. Asha here. In this video, I will explain you purine salvage pathway and its related clinical condition, that is Lesch Nyhan syndrome. So regarding purine nucleotide biosynthesis, we have two pathways. One is de novo synthesis and the second one is salvage pathway. So before going to the discussion part of salvage pathway, I will tell you something related to the structure of a purine nucleotide. So regarding the structure of a nucleotide, the nucleotide structure have three functional units. The first component is a base. Base means it is a nitrogenous base. So the base can be either a purine base or a pyrimidine base. So purine bases are adenine and guanine, and pyrimidine bases are cytosine, uracil and thymine. So pyrimidine bases are cytosine, uracil and thymine, and purine bases are adenine and guanine. And the second component is pentose sugar. So the pentose sugar can be either a ribose sugar or a deoxyribose sugar. And ribose sugar is present in RNA and deoxyribose sugar is present in DNA. And the third functional component is phosphate group. So these are the three functional components of a nucleotide. The first one is a nitrogenous base, the second component is a pentose sugar, and the third component is a phosphate group. Then you should know what is the difference between a nucleoside and a nucleotide. So as mentioned here, a nucleotide is made of three components, that is a nitrogenous base, a pentose sugar and a phosphate group. So these are the three basic structural components of a nucleotide. Here the base with a pentose sugar, that is together known as a nucleoside. So nucleoside is a combination of a nitrogenous base with a pentose sugar. And nucleoside with phosphate, that completes the structural component of a nucleotide. So nucleotide is nucleoside plus phosphate. So nucleotide is having three functional components. One is a nitrogenous base and a pentose sugar and a phosphate group. And this base with pentose sugar together known as a nucleoside, and this nucleoside with phosphate group, that is the nucleotide. And regarding the structure of a ribose 5-phosphate, so all of you know regarding ribose, it is a pentose sugar, and ribose 5-phosphate is produced in the HMP shunt pathway. So the major functions of HMP shunt pathway is, one is the production of ribose 5-phosphate, and the second one is for the production of NADPH. So ribose 5-phosphate is contributed by the HMP shunt pathway. And regarding ribose 5-phosphate, ribose is a 5-carbon sugar, and the fifth position there is an additional phosphate group. That compound is known as ribose 5-phosphate. So we have a pentose sugar, that is one of the structural component of a nucleotide, and we have a phosphate group, that is the another structural component of a nucleotide. So to produce a nucleotide, we need just a nitrogenous base. So by adding this ribose 5-phosphate to a nitrogenous base can produce the corresponding nucleotide, and this reaction is known as phosphoribosylation. So nucleotide require a base, nitrogenous base, pentose sugar and a phosphate group. So ribose and phosphate, they are contributed by ribose 5-phosphate, and when we add this ribose 5-phosphate to a base, we can produce the corresponding purine nucleotide. And this addition of this ribose 5-phosphate is known as phosphoribosylation reaction, that is addition of a ribose along with 5-phosphate. So addition of this ribose 5-phosphate is known as phosphoribosylation reaction. So phosphoribosylation of a purine base result in the formation of corresponding purine nucleotide. Is it clear? So phosphoribosylation of a purine base can result in the formation of corresponding purine nucleotide. Similarly, if it is a nucleoside, so nucleoside is made of a nitrogenous base with a pentose sugar, and for the formation of nucleotide we need an additional phosphate group. So phosphorylation of a nucleotide result in the formation of nucleotide, corresponding nucleotide. So phosphorylation of a nucleoside result in the formation of corresponding purine nucleotide. Let's come to the de novo synthesis. So what is a de novo synthesis? In de novo synthesis, a purine nucleotide is synthesized from their precursor molecule. So what are the precursor molecule? One is purine base, second one is a pentose sugar, and third one is a phosphate group. So all of you know regarding a purine base, the different atoms of this purine bases are contributed by different amino acid. So that synthetic pathway is known as de novo biosynthesis. A purine nucleotide is synthesized from their precursor molecule. And this de novo biosynthesis is a highly energy consuming pathway. And the major regulatory enzyme in this pathway is known as PRPP glutamyl amidinotransferase enzyme. And this enzyme catalyzes the rate limiting step in the de novo purine biosynthesis. So PRPP glutamyl amidinotransferase enzyme, that is the major regulatory enzyme in de novo biosynthesis. And this de novo biosynthesis takes place in all tissues in our body. The major tissue is liver. And there are some exceptions. One is RBC, second one is WBC, and the third one is brain. So de novo biosynthesis does not take place in these three tissues, RBC, WBC and brain, because this tissue does not have this PRPP glutamyl amidinotransferase enzyme. That is the major regulatory enzyme of the de novo biosynthesis. So de novo biosynthesis takes place in most of the tissues in our body, and the major tissue is liver, and this pathway occurs in all the tissue. There are few exceptions. One is brain, the second tissue is RBC and WBC. The reason is this tissue does not have the regulatory enzyme of the de novo synthesis, that is PRPP glutamyl amidinotransferase enzyme. So these tissues, that is brain, RBC, WBC, prefer another pathway for purine nucleotide biosynthesis, that is salvage pathway. So salvage pathway takes place in brain, RBC and WBC. And regarding salvage pathway, actually this salvage pathway is a recycling pathway. This pathway reutilizes the used purine bases or a purine nucleoside for the formation of a new purine nucleotide. So a new purine nucleotide is prepared from a purine base or a purine nucleoside. And this pathway takes place in RBC, WBC and in brain. Regarding the salvage pathway, it is less energy consuming pathway compared to de novo biosynthesis. And this pathway is important in organ where de novo biosynthesis does not take place, that is RBC, WBC and brain. Because salvage pathway is important because all tissue needs nucleic acid. So in RBC, WBC and in brain, these nucleic acids are contributed by this salvage pathway. Coming to the reactions of salvage pathway, there are mainly two types of reactions in salvage pathway. If it is a purine base, then we need phosphate group and a ribose sugar. So these are the three components of a purine nucleotide, that is purine base, pentose sugar and a phosphate group. So if our bodies if the RBC, WBC and brain have used purine bases, this tissue can produce a new purine nucleotide by adding a ribose sugar and a phosphate group. This is done by donating a ribose 5-phosphate, because ribose phosphate contain a pentose sugar, that is ribose, and a phosphate group. And in this reaction, this ribose 5-phosphate is contributed or donated by a compound which is known as PRPP. PRPP means phosphoribosyl pyrophosphate. Then you should know how this PRPP is produced in our body. So PRPP is produced from ribose 5-phosphate and a phosphate group. Here the phosphate group is contributed by ATP. So PRPP is produced by the phosphorylation of ribose 5-phosphate. Clear? So by donating their ribose 5-phosphate, this PRPP is again converted into inorganic phosphate group. So for salvage pathway for the purine bases, PRPP donate this ribose 5-phosphate. By releasing their ribose 5-phosphate, this PRPP is converted into phosphate group. So coming to the reaction. So regarding phosphoribosylation reaction, and this reaction is mediated by an enzyme known as hypoxanthine guanine phosphoribosyl transferase or HGPRTase, because this enzyme catalyzes the transfer of ribose 5-phosphate from PRPP to two molecules. One is to the hypoxanthine, also to the guanine. So by receiving this ribose 5-phosphate, hypoxanthine is converted into their corresponding nucleotide, that is IMP, that is inosine monophosphate. And by receiving this ribose 5-phosphate, guanine is converted into GMP, that is guanosine monophosphate. And both these reactions are mediated by the same enzyme, that is HGPRTase, because they transfer ribose 5-phosphate from PRPP to hypoxanthine, also to the guanine. So this enzyme is very important, because the complete deficiency of this enzyme result in a clinical condition which is known as Lesch-Nyhan syndrome. And if it is a adenine is again another purine base. So if this RBC, WBC and brain has adenine as a purine base, this tissue can produce their corresponding purine nucleotide, that is adenosine monophosphate. Here also this tissue need ribose 5-phosphate, and this ribose 5-phosphate is contributed by PRPP. So PRPP donate their ribose 5-phosphate into the adenine, and this reaction is mediated by an enzyme known as APRTase, that is adenine phosphoribosyl transferase enzyme. That is, this enzyme transfer ribose 5-phosphate from PRPP to the adenine, and by donating their ribose 5-phosphate, this PRPP is converted into inorganic phosphate group, because PRPP means ribose 5-phosphate plus phosphate. So that is one of the reaction in salvage pathway. So in salvage pathway, if RBC, WBC and brain have purine bases, this tissue can produce their corresponding purine nucleotide, and this reaction is known as phosphoribosylation. And this phosphoribosylation require two different enzymes, that is HGPRTase and APRTase. Coming to the second reaction. If it is a purine nucleoside, if RBC, WBC and brain have used purine nucleoside, this tissue can produce their corresponding purine nucleotide. So here a purine nucleoside is converted into a purine nucleotide. So what is the requirement? The purine nucleoside already contain a purine base and a pentose sugar. The additional group is a phosphate group. So here it is a phosphorylation reaction. And all of you know regarding phosphorylation reaction, this phosphate group is donated by ATP, and the enzyme is known as kinase group of enzyme. So here adenosine is a purine nucleoside. So adenosine kinase enzyme catalyzes transfer of one phosphate group into the adenosine. So adenosine nucleoside is converted into their corresponding nucleotide, that is adenosine monophosphate, and ATP by donating their phosphate group, it is converted into ADP. So that is the second reaction in salvage pathway. So here a purine nucleotide is synthesized from a purine nucleoside, and the reaction is phosphorylation reaction. So these are the two reactions in salvage pathway. So if it is a purine base, the reaction is phosphoribosylation, because purine base require ribose 5-phosphate for the formation of purine nucleotide. And if it is a purine nucleoside, then the reaction is phosphorylation, because a purine nucleoside require an additional phosphate group for the formation of their corresponding purine nucleotide. That is phosphorylation of purine nucleoside and phosphoribosylation of purine bases. So that's all regarding the salvage pathway. Coming to the clinical condition related to the salvage pathway, there is a clinical condition which is known as Lesch-Nyhan syndrome. So you should know what is the biochemical defect in Lesch-Nyhan syndrome and what are the clinical features of Lesch-Nyhan syndrome. So first of all, you should know what is the inheritance pattern. Here the inheritance pattern is X-linked recessive inheritance. So only the males are affected and females are only carriers. So the inheritance pattern is X-linked recessive inheritance. And the biochemical defect, it is due to the deficiency of HGPRTase enzyme. Actually, Lesch-Nyhan syndrome is due to the complete deficiency of HGPRTase enzyme, because partial enzyme deficiency produces just hyperuricemia. So complete deficiency of HGPRTase enzyme produces Lesch-Nyhan syndrome. That is the biochemical defect in Lesch-Nyhan syndrome, and all of you know regarding HGPRTase, that is the main enzyme in purine salvage pathway. And one of the clinical manifestation of Lesch-Nyhan syndrome is hyperuricemia. So let's see how this patient develop hyperuricemia. So in this patient, there will be complete deficiency of HGPRTase enzyme, and this HGPRTase enzyme is the one of the major consumer of PRPP. So what is PRPP? Ribose 5-phosphate plus phosphate. So whenever there is a defective purine salvage pathway, our body produces more and more PRPP. So all this leads to accumulation of PRPP in our body. So PRPP gets accumulated in our body. And this PRPP, what is the next metabolic fate of this PRPP? This PRPP is now channeled into the de novo purine biosynthetic pathway. So in de novo purine biosynthetic pathway, through this de novo biosynthetic pathway, it produces purine nucleotide. So there will be more amount of purine nucleotide, and all this purine nucleotide undergo catabolism. And the catabolic end product of purine is uric acid. So there will be more and more catabolism. All this produces high amount of uric acid in blood, and that condition is known as hyperuricemia. So Lesch-Nyhan syndrome patient will having high blood level of uric acid, that is hyperuricemia. The reason is there will be complete deficiency of HGPRTase enzyme, and HGPRTase enzyme is the major consumer of PRPP. So that will result in the accumulation of PRPP, and PRPP now channel into the de novo purine biosynthetic pathway. So there will be more and more purine nucleotide, and all this purine nucleotide undergo catabolism, and it will produce more and more uric acid. So regarding clinical features, one of the clinical features is hyperuricemia. So this uric acid have a tendency to produce stones in the urinary tract. So that will produce urolithiasis. So that is one of the clinical feature in Lesch-Nyhan syndrome. And this excess uric acid may deposited in the joint cavity and also in the soft connective tissue. And that condition, it is known as gouty arthritis. So gouty arthritis and urolithiasis, all these are due to hyperuricemia. And the second clinical feature is the affected children having a specific neurological deficit, that is they having muscle spasticity and mental retardation, because brain require nucleic acid for their development, and brain purely depends on salvage pathway. So in Lesch-Nyhan syndrome there will be defective salvage pathway that result in deficiency of nucleic acid in brain. That's why this affected patient will develop mental retardation and muscle spasticity. And the third clinical feature that is specific for Lesch-Nyhan syndrome, that is self-mutilation behavior. The affected children often make injuries on their own body. They often bite their fingertips and lips. So they make injuries on their own bodies, especially in the fingertips and in the lips. So that behavior is known as self-mutilation behavior. So self-mutilation behavior, mental retardation and hyperuricemia, all these three clinical features suggestive of Lesch-Nyhan syndrome. Regarding treatment, there is no definitive treatment for Lesch-Nyhan syndrome. We can give allopurinol to reduce uric acid production. So let's see one clinical scenario. Here a patient is presented with mental retardation and is having self-mutilation behavior, and on examination spasticity was present, and blood examination showed high serum uric acid level, and monosodium urate crystal were seen in aspirated synovial fluid. So synovial fluid cytology shows monosodium urate crystal. So here the affected patient is having mental retardation, self-mutilation behavior, muscle spasticity and high blood level of uric acid. So all these features suggestive of Lesch-Nyhan syndrome. So that is the answer. So what is the biochemical defect? Here the biochemical defect is complete deficiency of HGPRTase enzyme, that is hypoxanthine guanine phosphoribosyl transferase enzyme, and that is the major enzyme in purine salvage pathway. So that's all regarding purine salvage pathway and Lesch Nyhan syndrome. Thank you.